she could sit in classes, and ultimately the dean said no.
No?
Yeah.
Wow.
Because it would appear to be favoring, it could favor one political group over another one.
Oh.
And he felt that was inappropriate.
Oh, yeah.
I thought, why not? But,
Yeah.
but I made the mistake of asking the dean. Oh. Okay. No words of wisdom?
Words of wisdom? Happy Friday.
Good enough. I'm okay with that. Well, good. Well, we were spending time on gas chromatography, obviously, and we're going through different detectors. Basically, what comes out of the column, how do we detect it? And we'd done kind of the workhorse for that, and that was flame ionization. Did kind of the universal detector, which was the thermal conductivity. And then we're getting into more specific detectors. And so this is one of those detectors, which is electron capture. So electron capture, everybody's watching you instead of this. So either go sit down or write quickly. Go ahead.
I'm being distracted.
Okay. I'll remember that. So, okay, now we're looking at this direction. So we've got our analytical column coming up here. Compounds are eluting out. They're flowing with the gas out into the room, as always. And it's electron capture. So the inside of this chamber is coated with tritium. And that's a radioactive isotope that gives off electrons in its degradation, its radioactivities. And so we've got constant flow of electrons here to a ground. And so we have a flow of electricity from the wall to this post. And so that's a constant, 24 hours a day, all the time. It's radioactive decay, giving it off, adding electrons. If an organic compound comes out here that happens to like electrons, absorbs electrons, it decreases the electrical flow. And basically, what you're getting is a response. You've got a constant electrical flow, oh, it decreases. And so you kind of draw the peak down, but you turn it so it's up instead. So it looks more aesthetically pleasing. How's that? And so, like I say, anything that absorbs electrons are what it does detect. Well, what that means, halogens, conjugated carbonyls, nitriles, a few other. No response to ordinary organic compounds, no response to water. You look at specificity, where did it find its use? Really in pesticides, herbicides. Some pollutants, PCBs as an example. So this is the detector that gives you specificity and pretty decent sensitivity. I think about it 10 to the minus 14th grams. Now, gram isn't a lot. Break that into 10 to the minus 14th, and it's a tiny amount. So it's really excellent sensitivity. So it's somewhat specific. It's very sensitive. Linear range, well, only linear over change in concentration of 10,000. That seems pretty good, but it doesn't worry rate some of the other detectors. They do have definite temperature limits. If you warm that up too much, the tritium volatilizes, it goes into the room, and that's not good. So anyway, there are things they have to look at when you use this detector. This is another specific detector. In this case, what we do is we do have our capillary columns, our columns coming in, dumping compounds into more or less of a plasma. That plasma has some reagent gas, and so certain elements react with that reagent gas to give off basically a wavelength, a signal, a light signal. And that light signal gets measured by a photomultiplier tube. And so basically very specific. Anything that has sulfur gives off the wavelengths we're interested in. We don't see anything else. We just see sulfur. So again, very specific and very, very sensitive. Flame photometric does somewhat the same things, except this is just a normal flame ionization. And you've all done atomic emission, haven't you? one way or another, or you will. Basically, you know, atomic emission, so we're giving off a wavelength and measuring that wavelength. Okay, if you go to the Science Museum down the bottom floor, you turn right at the stairs, you can draw in different, metal solutions. It draws the metal solution into the flame and it gives off different light, different wavelengths. And it's exactly the same principle here. As you burn compounds, they give off different wavelengths of energy. And then you've got a filter here that only allows sulfur, or I think it's nitrogen too. And so we've got basically specificity again. Things that are specific make cleanup less important. We have to spend less time to make things clean or pure. So it does save us in terms of sample preparation as well. We've had infrared detectors. They've largely gone out of use. They were good for some compounds, specific, but we just found other ways to deal with that. So if you ever hear of FTIR coupled with GC, not anymore. This is what's been the major change in detectors. They're starting to use mass spectrometry as a detector. You'll deal with that as a subject. We'll talk about mass spectrometry in itself, but here we're coupling it to a gas chromatograph. So as each compound elutes from the gas chromatograph, it goes into the mass spectrometer, and that's our detector. And I'll say a little bit about this. And this is, there's a take-home message in here I don't want you to forget. So this is your total ion chromatogram. It's equivalent to the gas chromatogram. It draws, oh, here comes a compound. Okay, there's so much and so much. And that's the total ion chromatogram, similar to your normal gas chromatogram. This is one little segment of this. There's a little bit of peaks down here. Even if you're close, they're small. And if you enlarge that, then this orange one is what you see. You see it drawn, and you don't see any of these other colors in here, and I'll explain what the other colors are. Is that for flame ionization, in the other one you'd see this peak come up, and you'd say, oh, that's one compound, right? Oh, it's one peak. Gosh, it looks nice and symmetrical. Oh, that's neat. But if it's possible to look under that peak and say, where did that total peak come from? You start finding, oh, there's one compound here, but there's another little one here, another one here. This peak, which looks like one peak, no, it's this plus that plus that plus that. And so mass spectrometry starts giving you the opportunity to actually take this apart and see what's making those peaks. All the other detectors, you draw something like that, and you don't know what's underneath that. You don't know what resulted or produced that peak. And this is just, again, taking the one example up here. And what the mass spectrometer does is it takes each of your compounds as they come out of your gas chromatograph, hits them with 70 electron volts electrons. It's a tremendous amount of energy. And it blows those compounds to bits. But every compound will fragment a little different. The pieces you get for each compound tends to be unique. So every compound, like I say, has a unique bunch of pieces. And then we start looking at those pieces. Oh, these pieces here, they fit together for one molecule, and they then are here. Another set of pieces fit together for another compound here. And you can start detecting compounds and quantifying compounds without ever separating them. They're not separated. These compounds aren't separated by gas chromatography. But the detector learns and says, okay, these set of pieces, they're following, I'm measuring them, that's what I'm measuring. And so the neat thing is now, you don't have to separate compounds to measure them and quantify them. So we've got a tremendously powerful tool for separation gas chromatography. Now we put together a detector that says, don't worry about it. If you separate it by 100th of a second, I can figure it out. And that's what makes it just tremendously powerful. This is taking, this other part into pieces, and maybe we won't spend so much time with it. But what you would find is that when you blow this peak number 37, when you blow it into bits, these are the pieces that that molecule gives up, peak 38, which isn't separated, blows into these kinds of pieces. So the instrument really takes that set, and follows them together and draws a peak. Then you can measure and you can quantify. So it's really, really a powerful tool. It's a tremendous addition to any kind of analytical chemistry. And at one time, these instruments were, well, maybe the half the length of the row here, make it about that much wider, and you'd have them this high. And now, of course, they're that big by that big. And instead of being an arm and a leg and more for this big monster, it's something you can afford. They get into the $50,000 to $80,000. That's affordable for what it does. So moving on, that's detectors. Tremendous sensitivity, tremendous specificity, and ability to improve resolution or separation. But let's go back to the idea of improving separation. So when we run a sample on any tool, any technique, and we want to separate them, it really takes some time, and maybe we can go ahead and separate two things and we can measure them accurately. But the better we can separate them, the faster I can run them, the more I can push them together, I can save time. I'm out to get my best separation, absolutely the best separation I can in the shortest amount of time. And so we work with this idea of resolution. Let's make it good. Let's make it great so I can have quick analysis. I can take maybe an hour analysis and make it run in 9 minutes. Guess what? I can do 10 times as much. So this is what we work with. How do we improve resolution, separation of compounds in gas chromatography? And so we have this equation that I don't think you have any reason to remember, but I hope you get it. Oh, no, you're going to tell them it's important.
I told them it's important, but they don't have to remember the numbers.
Okay, that's really an important equation, but you don't have to remember the numbers.
So they need to know the factors, selectivity, capacity.
Absolutely. Okay. However, I have too much fun at this. Okay, so this is the equation. We really want the best separation we can, and these are the factors that we tend to work with. These are different terms, and I'll talk about how we make that term the best, how we make that term the best, and that term the best to improve our separation and make that separation fast. So in terms of that equation, we typically look at selectivity, capacity, and theoretical plates. Now, so sometimes you're going to go through them or have gone through them. Okay. Experts already. Good, good. But this kind of, they deal with different elements. Some of them relate to how well the compound interacts with your stationary phase. If your compounds don't have any interaction with that stationary phase, you don't get much interaction, you don't get much slowing down, much separation. Another term relates to how long does that compound spend in the column? How much interaction does it have again? But in the end, this is the one that tends to be most important of those parameters. Assuming you're somewhere reasonable in here, that's the one that we work with a great deal. And that's looking at theoretical plates. So theoretical plates, what we're really doing is we're looking at how well a compound stays together during your analysis. We make an injection, all of our compounds together is a nice sharp plug, and we want them to stay as a sharp peak. They stay together. Each set of compounds should stay together. And like I say, we work with that. That'll become more obvious as we take a look at this. So the idea of column efficiency, what are some of the things we work with? I've told you that these columns that we use can have different diameters. They can be very small columns, like 0.1 millimeters, all the way out to 0.75 millimeters. So do we want a really tiny column, or do we want a bigger column? And so if we're really interested in separation, and we're now measuring this over here in terms of number of plates, our column efficiency. So we want a large number here. The larger the number, the better our separation. And so if we look at how do we get our best separation, how do we get up here? Use tiny columns, very, very small diameter columns. The wider the column, the fatter the column, the poorer our separation. So if we want separation, we really want fine columns. That comes at a cost to us because our very, very small columns, we can't put much material on them. They would simply flood. You'd flood that stationary phase and your separation would become very poor. So if you're down here, you can't put much material on the column, a very small injection. And then you may want or may have a problem with detecting. It isn't enough to detect. So great separation, but lack of sensitivity. Out here, you'd have a lot of material. You can detect it, but it's poorly separated. So what do we do, of course? We go for kind of the middle of the road. Most of the time in gas chromatography, you're going to work in this general area, 0.2 to 0.25 millimeters inside diameter. So that's our range. So we've still got really good separating properties, but also we have fairly substantial quantities that we can put on the column. So column diameter, extremely important to us. The smaller it is, the better our separation, but it's a compromise in terms of quantity. Your mobile phase. This is really an interesting one to me because, you know, again, so you've gone through the equation relating mobile phase velocity versus separation. This is a different measure of separation. For the last one, we wanted a large number. For the height equivalent per theoretical plate, we want a small number. And so this one we want to minimize. They're just two different ways of looking at efficiency. And so if we kind of look across here, what mobile phase should we use? So what gas should we use? Should we use nitrogen? Should we use helium? Should we use hydrogen? Three very common gases that we could use. And if we look at this plot, and there is a relationship, obviously, between linear velocity and this term here, HETP, we find there's a minimum. This is our best separation, absolutely our best separation. But your carrier gas velocity is 10 centimeters per second. That's how fast the gas is going through. It's moving 10 centimeters through a column every second. That's very slow. If our mobile phase is slow, our separation is slow. So we say, no, we'd really like to work 20, 30, 40, 50 centimeters per second. I'm getting my materials through in a hurry, but my separation then isn't good. So nitrogen theoretically is the best material to use. It's lower, so better, than either hydrogen here, or helium. But then we have to run slow. If I change to helium, which many people do then, well, it never is quite as low. It's never quite as good as nitrogen. But you look and say, well, gosh, I can go from 10 centimeters per second, 20, 30, 40, here, even 50. And I've lost only a little bit in separating a power, very little. So I can get 4 times the carrier phase velocity. I could cut my analysis time by a factor of 4 by simply going from this to this, and I get about the same separation. So we like to use helium. It's very, very common. High velocity, but still have good separating power. But the champion over here is hydrogen. If you use hydrogen as the mobile phase, what's going through that column, look, I can go out here 50, 60, 70, 80, 90 centimeters per second. My separation is really fast, and I didn't suffer much for it. I could get almost the same separation at 90 centimeters per second as I do back here at 10 centimeters per second. My analysis time is only 10% what it was. So It's interesting to me in the industry, in most cases, people use helium. They use helium because what happens to hydrogen if you light it? It will match. If you're lucky, it does. It lights, explodes. But you have to be lucky, which is, well, I suppose you'd call it unlucky if it blew up. But from my standpoint, it's really hard to ignite hydrogen. There's only a small concentration balance between oxygen, air, and hydrogen that you can light it. Most other concentrations, they won't ignite. And so there's very, very little risk. There's a fear. It's like hydrogen-powered cars, right? People say, oh my God, remember the Hindenburg? Do you remember the Hindenburg, by the way? You do? You're not old enough. No. I'm old enough. No, maybe I'm not either, but but sure, the Hindenburg blew up, and it was filled with hydrogen, and for some reason that's plagued people's memories. And really taints the memory along those lines in terms of hydrogen cars and using hydrogen in analytical work. But it saves us a good deal of time. If it saves us time, it saves us money. And so if you go down to our laboratory, that's really all we run. That's the only carrier gas we run. It's cheap. It's cheaper than helium. It's cleaner than helium in terms of contaminants. And it saves us time. Going on, so okay, some of our parameters we were interested in. We're interested in the diameter of the column. We're interested in our mobile phase. Another one is, okay, that column has a coating on the inside. That's our stationary phase, the coating on the inside of that column. And so how thick should that be? Should it be a thick coating or should it be a thin coating? If we have a thick coating, that gives us more flexibility and concentration. We can put more materials on our column that can maybe help us with sensitivity if we put bigger samples on it. But it comes at a cost of separating ability. The thin phase gives us the best separation. So again, if we're really looking for efficiency, we want a thin column phase. So small diameter column, thin coating on the inside of that column. That gives us separation. That gives us rapid analysis. Column length is another parameter. What do you do when you're not getting separation? Very commonly, you just get a longer column. You put a longer one, gives us more opportunity for interaction. The problem with length of the column as a means of improving separation is that if I make my column twice as long, 30 meters instead of 15, it took me twice as long to do my analysis. And my improved separation, it takes me twice as long, but I only get 1.414 times better separation. It's a square root of the increase in length. So I double the length, double my analysis time, I get 1.414 times better separation. It's a poor way to get separation. It's costing you time. So what do you do when you have really problems, or we want to get, let's say, fast separations, efficient separations? You use small columns, you use thin phases, you use short columns as much as possible, you use rapid gas flow. So those things we've been talking about, what I've been mentioning, are things you go for. And never, ever assume that something you read is the best way to do it. And I say that because a lot of times the people that do this kind of work don't think about really these parameters. If they get a separation, they say, well, that's good. But they don't take time to optimize each of these parameters. So again, you kind of take it with a grain of salt and say, well, that's nice, but I think I can do better. So longer means better separations? Yep. But not much better resolution. So when you start thinking about this column and you start thinking about how I'm going to optimize my system, we really divide this into a triangle, or pyramid, I suppose we'd call it. And if we want resolution, we really have a tough separation. Man, I'm separating isomers that are very, very closely related. I need separation. It's not going to be done quickly. Separation ability is the opposite of speed. You're going to take time. If you're thinking about, oh, I want sensitivity and resolution, you're not going to get them. You're going to compromise sensitivity if you want speed. The idea of how big samples can I put on there, so maybe I can have better sensitivity in my system, it's going to cost us. So you don't get any one of these. You settle for a compromise. Your separations are easy. Hey man, you go for speed. You go that direction. Forget about these other things. So if it's an easy separation, you got speed. If you want a large amount of sample put on for some purpose, you go that direction. So you need to sit down and think about what you're doing, what your goals are, what the challenges are, and you then select the conditions to get those parameters. It's a fascinating technique, one I obviously enjoy a great deal. I've spent 6 hours with my grad students over the past month and a half going through this in detail, saying, okay, here's what we need to do, what we want to do, and how we do it. How's that? And it's fun. I suppose that sounds strange, but it is. Basic concepts, troubleshooting, problem solving. 80% of the trouble in a GC when you don't get good data, 80% of the time, it's because these gas flows don't go the right direction in the right amounts. We got a plumbing problem. You want to be into gas chromatography, you've got to be a plumber at heart, because you've got to make sure these gases are flowing in the rates you think and in the direction you think. So that's rather interesting. 80% of the time, there's a leak someplace, or something plugged, something that isn't working right. 10% of the time, it's the operator oversight, operator error. You screwed up. You didn't set things up properly, perhaps. 10% of the time, it's the GC. We've got gas chromatographs downstairs in our laboratory that probably got to 1980, and those things still purr like a kitten. They just operate without a moments of hesitation, reliably. If you know what you're doing with them, you can more or less, they don't fail this way, is what I'm saying. If they fail, it's because we screwed up rather than the instruments. What do you do? How do you know you're doing the best you can? How do you know your instrument is correct, giving you good data? Again, you run instrument quality control samples. And so you can inject known materials, known concentrations. You intersperse them with your samples and look and say, is your machine giving you the data that you expect? So, yep, you check that instrument. There is a difference between an instrument sample and a method control sample. In the method one, you put a sample someplace, you follow through extraction, isolation, cleanup, analysis. Did you get the data you thought? In this instrument, in this case, we're looking we forget all these steps beforehand. Does the instrument doing what you want it to? And so the idea that putting these things in, working them into your sample analysis routine is extremely important just to go ahead and check your instrument. There is another thing that I haven't mentioned here that is extremely important too, is that you can operate a gas chromatograph as a black box. By that I mean you put a sample and you get a number out, without any thinking in between those two processes. And every one of my students, when they run the gas chromatograph, they actually go to the what do we call it? Okay, wherever you look at, and you look at it, and you look and say, what did the instrument do? The instrument tells you when a peak is coming, and it tells you, oh, I'm starting to count that peak. I'm starting to measure. It gives you a little blip. It gives a peak, and then it gives you another blip. Oh, I stopped measuring that peak. Now I've gone on to something else. And they go through every one of those chromatograms, every one of the peaks, every one of the compounds they're analyzing. They look and say, did the instrument make the right decisions? Did it start when it should? Did it quit measuring the peak when it should? Sometimes there may be two compounds very close together. What did it do with them? Did it really go ahead and project? It tells you right on the screen what it did when I started stop measuring. Did it make the right decisions? otherwise, if you simply take the numbers without thinking about or looking at them, you can really run into some problems. So again, don't ever assume that the number that comes out on a piece of paper or on a computer screen, don't ever assume they're right. 99.9% of the time they are, sometimes they aren't. And then you can start saying, okay, why aren't they? Hardware failure, like I say, simply happens so rarely. It's unbelievable. It's generally us that screw up when this doesn't work. Where do we generally screw up if we start looking for problems? It's, like I said, in the flow of gases. As we mentioned very early in this game, we've got 54 mils per minute perhaps of our mobile phase coming in here, preferably, of course, now hydrogen, because we're being efficient. And normally it's set up so there's a nice seal up here, and some portion goes across here out of vent, and some goes down here and comes out that direction. Now there's a rubber septum up here, and you're going to sit there piecing this again and again with a syringe, and eventually it's going to leak. So again, you learn after a while, maybe every hundreds of samples, I take this top off and I put in a new septum, so I don't lose my gas to come out here, my sample to come out here. We kind of look and say, well, we normally don't mess with that, but maybe somebody did, So again, you check your flows. You check your flow here. There's making a seal between metal and glass here. And there's a nice little rubber O-ring there that keeps that metal and glass sealed together, so our gas doesn't go out this way, but in fact goes this way. I've taken these apart and have them be almost dust, that they've been so ignored and haven't looked after. There's another seal down here. So again, maintenance, looking after things, makes the difference on your chromatography, makes a difference on your data. And so I kind of highlighted each of the places where things can go wrong, but getting the gas going the right direction. This is the area that's under high pressure. Once we get to the column, it's under almost no pressure. You're not going to get leaks on this end. And to get the leaks here, we got pressure pushing on that column. So that's where you start looking through your system. That's where you do your maintenance of the system. Well, let's say I think about gas chromatography per se. There's a little bit about how you get samples into a gas chromatograph, and that's what we'll spend a bit of time at this point with. Now, how many of you have done gas chromatography as a laboratory? Some of you? Half the class? Okay. So you've worked with Cindy downstairs, fatty acid analysis, I assume? Yeah. But again, you look at different ways you can analyze gas samples. You can pick some sample up and put it in with a syringe of gas. You can analyze liquid samples. There's all kinds of ways to get the sample into a gas chromatograph. Again, how you do that will depend upon what kind of sample you have. One approach is, like I say, headspace sampling. Myson works with Pam, of course, and works in the area of flavors. He's looking at a headspace, but he has to concentrate that headspace a little bit before he can analyze it, before he can get enough material for the gas chromatograph to say. But if he had something that was a little more concentrated, he could simply put a sample in a closed bottle, put your sample inside, close the top with a nice septum, let it sit for 30 minutes, and of course, any volatile compounds will go into the gas, into the headspace, into the bottle. And he can literally just take a syringe, put it through the septum, drop some air, and go ahead and do his injection, called a headspace sample. So again, it's a fairly simple technique. So a sample headspace. We can do it simply that way, or we can go ahead and try to concentrate the compounds in the headspace above that sample. You've probably seen, those of you that have done the laboratory, you've seen SPME, I think, the solid phase microextraction. I think Cindy showed you kind of a big, looks like a syringe. And on the end of the syringe is a needle. That needle has an adsorbent on it. And you'll see that in your next slide. So kind of the syringe that she had, and then we'll see this a little bigger over here, is again more of the syringe, but there's this needle that will retract or be able to push into the headspace of the sample or drawn in. And that has an adsorbent on it. So I may be interested in oxidation of wheatgrass. How's that? And so you could put the intermediate wheatgrass into a bottle, let it come to equilibrium, put this into the headspace of the bottle, and it will absorb any volatile compounds that have come from the intermediate wheatgrass. It'll keep on absorbing, absorbing, absorbing. And pretty quick, I get this pretty well loaded. I pull it out and take it out, and I put it into a gas chromatograph and push this down into the heated part of the gas chromatograph, and it liberates the sample. So my sample is now free. A nice means of concentrating volatile compounds in a gas sample. Another choice is a twister. Again, you probably saw a twister. I think, or I hope Cindy had one. And if your male half hasn't seen it, you will. She'll say, "This is a twister." You'll say, "Oh yeah, I know that." And what that is, it's a fairly small glass stir bar. It's actually a quite tiny stir bar, and it comes right down to it. But that stir bar is coated with a dimethyl silicone absorbent. So you take this stir bar, you drop it into a sample, and anything that likes this coating is going to be absorbed into that stir bar. So you can stir your sample, whatever. At some point you pull it out of your sample, you put it into the gas chromatograph where it's hot. Flavor compounds, off-flavor compounds, pesticides, herbicides, come off into your analytical system, go into the column, and it's separated. So a stir bar, that's simply an adsorbent stir bar. So again, we've just got many ways we try to concentrate either gas samples, do extractions of liquid samples, solvent extractions, whatever, to get that in a form that we can do analysis on it. There's a couple examples we'll look at in terms of applications. So you're going through the fatty acid one. I think that shows up later. But here's just giving some examples of where we would use gas chromatography or do. My research area is flavor. I'm interested in flavor compounds. Most of the time I'm talking about volatile compounds you can smell. They're in the gas phase. I want to know what you're smelling. What makes you say that's a peach, that's a pear, that's a good beer, whatever you want. In one aspect of the flavor industry these days is looking at, of course, biotechnology, right, to make these flavor compounds. And so this is one patent that came about a while ago. Fermentation of oleic acid by a particular microorganism produces delta decalactone. Delta decalactone, if you would smell it, smells just like coconut. This can come from a tree, a bark of a tree, primarily grown in Indonesia, but it's expensive. It kills the tree, obviously, so people say, is there a better way, easier way to get coconut flavor? Well, you might say coconuts, but that's not very efficient. Coconuts don't have much coconut flavor, that just traces of it. I want buckets. I want milliliters, grams. That's a bucket. And so you do it through biotechnology. And so let's take a look at the next one for how it's done in a little bit more detail. And so a culture medium, so let's say you grow this culture, this organism produces these lactones. And so you can take that, put it into a separatory funnel, put some diethyl ether, shake it up, shake it up. The diethyl ether will separate. The diethyl ether is a better place for lactone. It doesn't want to be in the water. It doesn't want to be in the culture medium. It wants to be in that organic solvent. So you basically solvent extract your lactone into diethyl ether. You can go ahead and fractionate that a little bit by column chromatography and then do gas chromatography of it. And it's interesting that chiral compounds, remember they differ only in shape or configuration. is really a tough challenge. But again, in gas chromatography, it's done fairly simply. And so when this organism's producing the lactone, what is the chiral form of the lactone? Well, that's again monitored by gas chromatography. And so this would be showing the separation of delta decalactone and the unsaturated lactones, where we can separate the R and the S forms very nicely. That's tough to do, but it's done by gas chromatography. So we can isolate, determine how much we formed, what's the chiral form of that compound that's formed. Interestingly, because the R and the S forms have different sensory properties, different character. So again, you're having the organism form it, and then you check and see by gas chromatography how much is formed and which type is formed. Diphenylamine on apples, used to treat apples prior to storage to control apple scab. So apples are dipped in a solution of diphenylamine, 1 gram per kilogram of solution. Of course, we're interested in any residue that stays on that apple. The Food and Drug Administration permits 10 parts per million in the US. It's 0 tolerance in some countries. And so how do we analyze for that? Is there a residue on the apple? And this is again a fairly simple one. It's a surface residue, so it is going to be on the surface of the apple. So we can put the apples into a solvent. The solvent will extract off your diphenylamine, concentrate it, so you evaporate some of the solvent so we can concentrate our compound a little bit more. Concentrate and do gas chromatography, mass spectrometry. So do your extraction, concentration of your solvent, and then GC. And we do it by gas chromatography, mass spectrometry. This is what the flame ionization chromatogram would look like from the surface of your apple. You can think the next time you have an apple, you can think, man, I'm getting quite a selection of organic compounds on the surface of my apple. And we're not interested in the majority of them, but we are interested in this residue of diphenylamine. But which ones of these are diphenylamine? And can we guarantee that it's nothing else coming underneath it, that it's absolutely pure? And so that gets you into the mass spectrometry part. So if we go ahead and take a look at the mass spectrometry of the diphenylamine, these are the fragments. When diphenylamine goes into mass spectrometer, goes blow into bits. These are the bits it blows into. The mass spectrometer counts each of these fractions, each of these pieces it gets broken into. And a mass of 169 down here is fairly unique. Not many compounds break into a piece of mass 169. And so you set your mass spectrometer up, so it comes off your gas chromatograph, we get our compounds eluting, and it looks for any compounds that give 169 on being exploded. And so it's rather neat. This is an example of what your chromatogram looks like. You're blank, no apple. Here's an apple extract. And so we have all kinds of things potentially coming in here, but I'm only looking for 169. Oh, here's a compound that has 169. Okay, here's another one that has this piece 169. And the mass spectrometer, if I took a look at the whole bits of pieces, it says it's my diphenylamine. Here's one that's been spiked with 50 nanograms in 100 mils of diphenylamine. Comes along, and that's a sample extract, apple extract, and comes along, and it's that much bigger. So again, by looking at this is equivalent to having 50 nanograms per 100 mils, we can get an estimate of quantity here. But really neat, our mass spectrometer is eliminating all those other peaks. All that stuff you saw goes away because your mass spectrometer only looks for one piece of everything that's blown up in it. And so it gives you tremendous sensitivity. Fatty acid profile, that again, many of you have done. Must isolate a pure fat from a food. You might do that by a SOXLIT. It's fairly common. You're doing proximate analysis. You're going to be doing a fat extraction. Good, you have fat. You got pure fat for further analysis. And what you did, I believe you followed the same procedure. Take 3 milliliters of boron trifluoride, 2 drops of fat, 20 milliliter test tube. cap it, put the tube in boiling water for 1 minute. Boron trifluoride chops the fatty acid off from the glycerol. Remember what a triglyceride is? Glycerol plus 3 fatty acids. It chops off the fatty acids, separates them, and actually makes an ester out of it. It adds on this methyl group. And so we've made methyl esters of our fatty acids. We add a little bit of water to that, add a little bit of hexane, so the hexane will extract out these esters, concentrate them a little bit, and we can inject them into a gas chromatograph. How do you know what you have? So you're going to get a profile, right? You get a bunch of peaks. Well, what the heck are they? Well, you go ahead and buy standards, right? These are methyl esters. Methyl esters of butyric acid, caproic acid, caprylic, capric, lauric, myristic, right on down, or palmitic, right on down the line. And so by where this compound elutes in your gas chromatographic run, you know which fatty acid it is. Because a C6, hexanoic acid, is always going to come here, 3.258 minutes on this system under these conditions. So you run your standards, then you run your sample. And you will be able to say, oh, I've got this, I have that, that. And so by retention time, you know what compounds you have. By looking at how much, it gets us down into the area. This is measuring how big of a peak is that. The more compound you have, the bigger the peak. So the area of the peak, the size of that peak, relates to concentration. So again, your machine tells you this is what it is, which fatty acid it is, and this tells you how much it is. And this would be typically a chromatogram from fatty acids into vegetable oil. What do you find, of course? You find palmitic acid, stearic, and then we get into the unsaturated ones. So most of them, I think, most of yours probably look like this. Probably most of you did vegetable oil. If you would have done dairy fats, you would have found the short-chain fatty acids. If you do a palm kernel or coconut oil, you would have found some intermediate size fatty acids. But again, through gas chromatography, you can do a nice job of separating and quantifying, getting a fatty acid profile of your oil. This is just one that shows just a little more resolution. So this is stearic, oleic, linoleic, linolenic acid. So you can identify it. And hopefully that worked out for you, that you were able to do that in the laboratory. I don't think we need to do any more of that. That's kind of that. Okay.